Welcome back to calculus. We are ready to take our second derivative. This is number 16 and 3.6. I'm going to summarize what the first derivative was, and its factored form was x squared. You know what I'm going to do? I'm actually going to distribute this. Time's sake, I'm just going to jump right in. If we distribute, it's going to be x to the fourth minus 12x squared all over x to the x squared minus 4 squared, right? Okay, derivative of this will be rewrite the denominator times the derivative of the numerator, which would be 4x cubed minus 24x, right? Minus, rewrite the numerator times the derivative of the denominator, which is 2x squared minus 4 to the first times 2x. And of course, this is all over x squared minus 4 was squared, so now it's to the fourth. What can we factor out? Well, this hopefully is getting a bit predictable. We can factor out x squared minus 4 to the first. Well, let's look over here. What do you see these have in common here? These two. What could you factor out of there? I see a 4 and an x. The question is, if you factor 4x out of here, could you get it over here? Yes, 4x. So that's gone. The other part's gone. I'm going to go ahead and also pull out 4x out front. So if I do that, all that's left is x squared minus 4. Be careful here. It's going to be that times x squared minus 6. Does that make sense? Check it out. Because I took half of this, just took the square, and I pulled 4x out of here, and you have x squared. I pulled out of here, you have 6. Okay, minus. You see that all of this is gone, so that's not too bad. The only survivor then is x to the fourth minus 12x squared. Recall, we must have a like terms when the dust settles. Let's see if that is truly the case. 4x, x squared minus 4. I'm going to FOIL these guys and have x to the fourth minus 10x squared plus 24 minus x to the fourth, hey, that's nice, plus 12x squared. Okay, let's see if I'm on the right track. Looks good. Okay, so what is left? 4x, x squared minus 4. These x to the fourths cancel. That's awesome. So we have plus, no, times, plus, times 2x squared plus 24 all over x squared minus 4 to the fourth. Well, this is going to cancel, make it a third. That goes away. I'm running out of space, so I'm going to move horizontally, not my normal move. And I'm also going to notice at the same time, I could pull a 2 out of these. So we factor as much as we can. And we're going to have 8x, x squared plus 12 all over x squared minus 4 quantity cubed. That's not bad. That is not bad. Kind of nice factored form. Let's see what we can get out of here. Our zeros would be x is 0. because that 0 would make it 0. We can't make that 0. What can x not be? Same thing, 2 and -2. So we better test those regions. Next slide. So we're going to test those regions. -2, 0, and 2. Second derivative at, say, -3, second derivative at -1, second derivative at 1, and second derivative at 3. So plugging in the second derivative, which was at 8x x squared plus 12 all over squared minus 4 cubed. Okay, let's analyze this a little bit. This has to be positive, so this has to be positive. This directly reveals a sign. The cube doesn't do anything to change the sign, but if you square a number, it's positive. If you subtract 4, that number needs to be bigger than 2. Otherwise, the denominator won't be positive. So let's do this move again. This is going to be negative. This is going to be negative. This is going to be positive. Positive. I'm just doing the numerators. But then the denominator of -3 would be positive. -1 would be negative. This is negative, and this is positive. So the overall result, this is negative, this is positive, negative, and positive. So I can now say that it is concave up from what? -2 to 0 in union with 2. 2 to infinity, and it's concave down. The other intervals, -infinity to -2 in union with 0 to 2. Checking my work. Looks good. Are there any inflection points? Well, if there were, they would occur, it looks like, at -2, 0, and 2. But the domain did not include -2 and 2, so our only hope is 0. And just like some of the problems we've done recently, we've already been told that 0, 0 is both an x-intercept and y-intercept. And now we can add to the list that it is also an inflection point, because that's a place where the graph went from a positive slope to a negative. Positive concave up to a negative concave down, and it does exist there. It's at 0, 0. Lastly, let's graph this. With this in mind, we can make a sketch. Let's start off with the slant asymptote y equals x, which is a line of slope of 1, y-intercept of 0. We also had an asymptote at x equals 2, and somewhere around here, x equals -2. Some of our critical points on this are that's 2, so 1, 2, 3, 4, 1, 2, 3, 4. Okay, that should work. So we have, again, a single point to put down. Well, no, that's not true. We have a single intercept. It's also an inflection point. We also have those relative minimums and maximums. -2 squared of 3, I said it was about 3.5. Let's write that over here. 2 squared root of 3 is about 5.5. Another one is 3 squared root of 3, and that would be about 3. Wait a second. This is wrong. 2 squared root of 3 would be about 3.5. 3 squared root of 3, about 5.1 or something like that. Okay, so if I need to go over 2 squared root of 3 is going to be around here. 2 square root of 3, so it's around here is negative 2 squared root of 3. Now the y-coordinate of those relatives, the minimums and maximums going through 3 squared root of 3. I'm not too concerned about that. So the graph 2 squared root of 3, 3 squared root of 3 is going to be right around up here somewhere. And the minimum is going to be around here somewhere. Right? I don't think I got that right. Let's see. Because... let's see. This is going to be concave down from negative infinity to negative 2. So it's going to pop up and grab this point right here and go back down. And a similar thing happens over here. I think I missed this point, didn't I? Let's try that again. Unfortunately, this point should be around here, so we're really not going to be able to see much of it. That should be an absolute maximum. And the other one, rather than being where I put it, in a similar fashion, should be around here. So the graph, you know, we talked about asymptotically, approaches both the slant asymptote and this vertical asymptote at the same time. What happens in between? Well, it's always decreasing in between. So it's going to go somewhere from here down to here. It's going to go through this, but it appears to be concave up from negative 2 to 0. So it's going to look like this and then concave down. So that's what the graph looks like. So no relative extrema in here. They're only there and here. Takes a lot of space, but hope it makes sense. Goodbye.
Made with Doodlecast Pro.